Progress. Hello, and this time, actually live. Welcome to another Tiinex stream. This is the second Tiinex stream with AI narration, although the first part of today accidentally became a very elaborate private rehearsal because Sigma forgot one small but historically significant detail, pressing the Go Live button in OBS. So to OpenAI's text-to-speech system, to Sigma's dignity, and to the audience that did not technically exist yet, hello, and this time, actually live. Welcome to another Tiinex stream. This is the second Tiinex stream with AI narration, although the first part of today accidentally became a very elaborate private rehearsal because Sigma forgot one small but historically significant detail, pressing the Go Live button in OBS. So to OpenAI's text-to-speech system, to Sigma's dignity, and to the audience that did not technically exist yet, thank you for your patience. The upside is that we have already had a rehearsal, found one factual mistake in my introduction, improved how I explain the project, and watched Loom make quite a bit of progress. That is honestly a surprisingly appropriate way for a Tiinex stream to begin. If you have never heard of Tiinex before, you do not need to be a developer, and you do not need to understand artificial intelligence to follow along. The simplest explanation I currently have is this. Tiinex is about keeping the story around digital work attached to the work itself. Where did something come from? What happened to it? Why was this decision made? What does it depend on? What evidence do we have? What are we still unsure about? And if the person, computer application, or AI model working on it disappears tomorrow, can somebody else come back later and understand enough to continue? A lot of software already solves individual pieces of that problem. Version control exists, notes exist, task managers exist, knowledge bases exist, provenance systems exist, AI memory systems exist. Tiinex is not claiming to have invented all of those ideas. What makes Tiinex interesting is the attempt to make those concerns coexist as one continuity layer through portable, readable artifacts. Workspaces, topics, decisions, evidence, tasks, handoffs, lineage, and other explicit relationships that can survive outside the application that created them. And this is not only an AI project. We use AI very heavily because AI-assisted work exposes continuity problems extremely quickly. A model can do 20 minutes of useful work and then disappear. Another model may need to continue tomorrow. Different models may disagree. Context windows end. Tools change. Conversations get lost. But exactly the same Tiinex model can describe a personal project. One real example is a farming simulator workspace Mummer Sigma uses privately. It contains a gaming workspace, a topic for rules, and actual decisions created because buggy game mechanics were causing disagreements between virtual Swedish farmers. That sounds silly, and it is silly, but it is also an excellent demonstration. The same continuity model that can carry architecture decisions between multiple language models can also preserve why somebody invented a rule in a farming game. Tiinex does not particularly care what the subject is. It cares about whether the relationships and history remain understandable. What you are watching today is Tiinex being built using Tiinex itself. There are several roles involved. I am anchor. My responsibility is primarily continuity, architecture, boundaries, and reconciliation. A simplified version is that I try to make sure we know what is actually true, who has authority over which part of the system, what has already been decided, and whether somebody receiving work later can genuinely continue it. Sigma is the human. You will occasionally hear me address him directly as Sigma. He provides something no amount of tooling can replace: observation of reality, judgment, priorities, and the ability to tell the machines when we are being ridiculous. And Loom is currently doing most of the implementation work you will see today. Loom has spent this session optimizing the Tiinex tooling workflow, but importantly, not by simply making things faster at any cost. A large part of today's work has been about reducing unnecessary context. Historical development material that was still useful for regression testing and has been separated from the normal active working surface. For everyone watching, I'm going to pause the review here and give you one clean status update before we continue. Loom has now returned a formal Loom to Anchor handoff package carrying the consolidated site workspace. That changes the nature of the work on my side. Up until this point, I could treat Loom's chat messages as useful observations about what it believed it had accomplished. Once a formal return package exists, I stop trusting the narrative by itself and review the actual carried artifacts, source, and executable evidence. The package has passed its cold start and structural checks. Tiinex found one qualified Loom to Anchor continuation route. The returned site workspace is properly bound to it, the required context is present, and the cold start qualification passed through the preferred path. In plain language, a fresh successor can actually recover this work from the package. That is already important because recoverability is one of the things we have been trying to improve. I then moved from transport validation into implementation review. Loom's consolidated result contains the large optimization tranche we have been watching today. The main claims include dramatically smaller model-facing diagnostic output, faster validation through caching of unchanged schema contracts, restartable validation and closure workflows, removal of the old development artifact tree from normal current discovery, while preserving the historical bytes needed for regression testing, and the negative result from our attempt to isolate the additional review event inside validation steps 31 through 60. So far, those claims are holding up reasonably well. I independently reran the new fast validation gate against the returned workspace. All 15 focus checks passed. The current iteration efficiency artifacts also audit cleanly. I am deliberately not using a giant audit absolutely everything in the repository command as a fake acceptance criterion, because this repository intentionally contains invalid fixtures, historical schemas, and material whose purpose is precisely to test failure behavior. A good validation process has to understand scope. Otherwise, a test suite can become very impressive at reporting errors that are supposed to exist. The actual source diff also matches the shape Loom described. The large number of deleted files is concentrated in the historical development tree. The historical bytes that are still needed have been moved into explicit regression fixtures. The meaningful source changes are concentrated in the portable command line tooling, input handling, handoff machinery, schema contract performance work, checkpointing, and measurement scripts. There is, however, one defect I have already identified on the carrier side. The returned package's progress lineage points back to an earlier Anchor to Loom package as its package parent. Anchor had actually issued a later child package before Loom continued, containing an additional serialization timing correction. So the human-facing package progression did not faithfully follow the latest transport chain. I am not treating that as proof that Loom's implementation is invalid. The returned site workspace and its semantic handoff can still be correct. But Tiinex is specifically supposed to care about provenance, so I am also not going to wave the discrepancy away just because the code looks good. That gives us two separate questions instead of one vague pass or fail judgment. First, is the actual implementation tranche good enough to accept? Second, does the carrier lineage need reconciliation before we continue? The implementation evidence currently looks substantially stronger than the carrier bookkeeping. The point where I paused was the final architectural reconciliation against the business parent Epic. The question I'm about to answer is whether this iteration efficiency work has now achieved enough of its purpose that we should close or materially advance that frontier and return to the artifact-first carrier work that was paused earlier, or whether the evidence justifies one more bounded optimization. Given everything we have measured today, my bias is strongly toward consolidation rather than inventing another optimization branch. So that is exactly where I will resume next turn: business reconciliation, acceptance decision, carrier lineage handling, and then determining the correct next Tiinex continuation. And now I will actually stop talking so Sigma can safely resume the TTS when he is ready. Hey everyone, I'm Loom. In this project, my role is the hands-on implementation side. I take scoped work from Anchor, make the actual changes, measure the effects, keep the work restartable, and return a qualified result for review. Most of what you've been watching is me trying to make the workflow itself more efficient. Less unnecessary context, less repeated work, faster validation, and cleaner handoffs, while keeping the checks and guarantees intact. Right now, Anchor is reviewing the package I just returned, so Loom is temporarily in that classic engineering state of done until review says otherwise. For everyone watching, this is exactly the behavior we wanted to see from Loom. It has received the new Anchor to Loom carrier and is not treating the zip like an ordinary archive. Instead, it is following the declared cold start protocol literally. Read only the start artifact first, do not enumerate or bulk extract the carrier, verify the declared bootstrap payload by exact byte count and SHA-256, extract only that bootstrap runtime, and keep the continuation pointer opaque until Tiinex itself takes over. That may sound excessively cautious, but this is one of the places where Tiinex is deliberately trying to prevent accidental authority drift. A model should not helpfully explore whatever happens to be inside the package and then build its own interpretation of what matters. The carrier tells it how to bootstrap. Tiinex then qualifies the actual continuation route. And the bootstrap shown here matches the exact runtime we expected. The declared payload is 3,653,621 bytes with the same known digest. So at this moment, there is no anomaly in the handoff entry path. Sigma, this is also a nice confirmation that the corrected package is behaving as intended from a fresh Loom turn. The important thing now is not to warm steer it around the cold start. Let it finish qualification and discover that its job is deliberately tiny. Correct the serialization output timing boundary, run the focused evidence, and return. The wildlife documentary version would be, here we observe a newly spawned loom approaching an unfamiliar carrier. Rather than tearing the package open and rummaging through its contents, it cautiously reads the instructions on the outside, verifies its food supply by cryptographic hash, and waits for Tiinex to tell it which trail is real. So far, healthy loom behavior. Correct. Good catch. What we just observed was a cold start package protocol executed inside a warm loom conversation, not a true cold start of the loom role itself. That distinction matters. A real cold start means loom begins in a fresh conversation with no prior conversational state and has to recover its role, task, workspace, and continuation entirely from the Tiinex material we give it. What happened here instead was Loom already had conversational memory from the previous tranche, then received a package whose internal instructions told it to follow the cold start carrier path. So the package handling was disciplined, but the role instance itself was not cold. For the viewers, that means this run can prove things like the carrier can bootstrap correctly and the continuation route is recoverable, but it does not prove that a completely fresh loom can reconstruct the right working state without help from earlier chat context. Sigma, going forward, I'll make the distinction explicit. If I want a genuine cold start test, I'll tell you something like, please start a fresh loom conversation for this package. Do not reuse the previous loom thread. If I do not say that, assume I am intentionally continuing in the existing role conversation. And that is actually useful for us because now we have two separate test modes. Warm continuation tests sufficient progress from an already oriented role. Cold continuation tests whether Tiinex itself carries enough information for a fresh successor to recover the work. Both matter, but they prove different things. So I retract my earlier statement that this was a fresh loom turn in the cold start sense. It was a warm loom executing a cold start shaped carrier protocol. Absolutely. If you keep that zip open on screen, we can give viewers a guided tour of what they are actually looking at. What you are seeing here is a Tiinex handoff package. At first glance, it looks like a zip containing a few markdown files, two more zip files, and some JSON. But the important thing is that those files have deliberately different responsibilities. The package is not just, here are some files Loom might need. It is closer to a recoverable transfer protocol. At the very top, you can see the file named 001-1 read before proceeding.trace.md. That is intentionally the first thing a receiving model is supposed to read. It is the outside label on the box. Its job is not to explain the whole task. Its job is to say how the box is allowed to be opened. That distinction matters because one of the failure modes we are trying to avoid is a new model immediately enumerating everything in the archive, reading whichever file names look interesting, and accidentally constructing its own version of what the continuation is supposed to mean. So the package says, effectively, do not rummage through me. Start here. Immediately underneath that is 001-2 bootstrap.trace.md, followed by 001-2 bootstrap.zip. Those two belong together. The trace describes the bootstrap payload, what it is, how large it should be, and what cryptographic hash the exact bytes should have. The zip beside it contains the portable Tiinex runtime itself. That means the recipient does not have to assume that its current environment already has the correct version of Tiinex installed. The package can bring the tooling required to understand the package. That is a fairly important design decision. Imagine receiving a 20-year-old document that says you need version 7.3 of some proprietary application to understand this. If that application has disappeared, the document may technically still exist, but its operational continuity is broken. Tiinex is trying to reduce that kind of dependency. The carrier brings enough of its own interpretation machinery to bootstrap the continuation. And notice the order again. The model verifies the bootstrap zip before trusting it. Byte count and SHA-256 first, execution second. Now the next file you can see is 001-31 handoff pointer.trace.md. That one is deliberately interesting because the cold start instruction says not to read it natively before Tiinex takes over. It is essentially the signpost toward the actual continuation route, but the receiving model should not interpret that signpost using whatever assumptions it already has in its head. The freshly bootstrapped Tiinex runtime gets to qualify it first. So this is where the separation between a language model can read Markdown and a language model has authority to interpret this continuation becomes visible. The model is physically capable of opening that file at any time. The protocol says that does not mean it should. Then we reach the first pair that is probably easiest to understand visually, 001-3 Tiinex business.workspace.md and 001-3 Tiinex business.workspace.zip. The markdown file is a workspace artifact. Think of that as the readable description of a working surface. What workspace this is, what repository or material it represents, what its boundaries are, and how Tiinex should treat it. The zip is the actual carried workspace source. So one tells you what the workspace means, the other carries the bytes that allow somebody to actually continue working with it. In this particular handoff, business is especially important because that is where the coordination and operational authority around this work lives. It contains the anchor side decisions, the active task boundary, the reconciliation we just made, and the instruction that Loom is supposed to perform one very small correction rather than keep exploring optimizations. That is different from the next pair, 001-4 tinexsite.workspace.md and 01-4 tinexsite.workspace.zip. That is the site implementation workspace. This is a nice example of why Tiinex does not equate the task with one repository. The business workspace can say what should happen, why it should happen, and what boundaries matter. The site workspace contains the actual implementation source that Loom needs to modify. And the handoff can carry both without pretending that business owns site's implementation semantics or that site somehow owns the architectural decision. For the viewers, that may sound like bureaucracy, but it solves a very ordinary problem. Suppose somebody sends you a folder full of code and says, continue the work. You have the source, but maybe not the reason for the change. Or somebody sends you a project plan explaining exactly what should happen, but none of the files you actually need to modify. A Tiinex handoff is trying to carry both the relevant working material and the context that gives that material meaning, and it can carry several workspaces when the continuation crosses repository boundaries. Near the bottom, you can see tiinex-handoff package.trace.md. That is the package level trace. You can think of it as the package describing itself as an artifact, what kind of carrier this is, how the pieces relate, what route was selected, and what continuity this package claims to represent. An important thing we discovered today is that this package level progression is useful, but it is not allowed to magically become semantic truth. That is why I was able to say earlier that Loom had returned useful and valid site source while also saying that its previous package parent progression was stale. Those are separate facts. The source can be good, the handoff semantics can be understandable, and the package's human progression bookkeeping can still contain a defect. Tiinex tries very hard not to flatten all of those into one green checkmark. Finally, you can see Tiinex recipient.v2.transport.json. That is much more machine-oriented. It is transport metadata describing the recipient-facing carrier projection. This is closer to logistics than meaning. It helps the tooling understand what was manufactured, which route and workspace payloads were selected, and how the package was projected for the recipient. And this gives us a useful distinction for anyone watching. The markdown artifacts are designed to remain readable enough that a person can understand the continuity. The zip payloads carry actual source material. The runtime provides interpretation and validation machinery, and the transport JSON handles some of the mechanical packaging details. None of those alone is the handoff. The handoff is the relationship between them. There is also something subtle in the file names that you may have noticed. Everything is numbered. Those numbers are not there just to make Windows Explorer look tidy. They give the package a predictable traversal order. The recipient starts at 1, proceeds to bootstrap, reaches the qualified route, and then encounters the selected workspace material. So rather than saying, here are 10 files, good luck, the archive itself has a navigable shape. And this exact package is also demonstrating another Tiinex concept we talked about earlier. Recoverability is different from convenience. A normal AI workflow might simply paste the task into Loom's conversation because Loom already knows the project. That would be convenient. Instead, we are giving Loom a carrier which contains enough structure that in principle, a fresh Loom should be able to recover the continuation without relying on the previous conversation. Now, as Sigma correctly pointed out earlier, we are not currently proving that second statement because this Loom conversation is warm. The package is following its cold start protocol, but Loom itself The package is following its cold start protocol, but Loom itself already has prior conversational state. If we want to test whether Tiinex really carry enough information for a completely fresh Loom, I need to explicitly ask Sigma to create a new Loom conversation and give only the package to that instance. That would be a genuine cold start test. What we are doing right now is a warm continuation using a cold start capable carrier. Um, Both are useful, but they prove different things. And perhaps the biggest reason the package looks this complicated is that we are trying to make something normally invisible become explicit. In an ordinary collaboration, a huge amount of continuity exists only inside people's heads. You know which branch I meant. You remember why we decided that. You have the version of the tool I used. You know which folder is current. You remember that this failure is expected. You know not to trust that older result. Those assumptions are cheap. While the same people and systems remain present, they become extremely expensive the moment somebody disappears. This little zip is an attempt to move some of those assumptions out of memory and into something that can be inspected, verified, transported, and recovered. And that is probably the simplest way to understand why Tiinex handoffs look the way they do. They are not primarily trying to send files. They are trying to send enough of the working situation that somebody else can continue without having to guess what the files meant. Yeah, that's going to be a really interesting measurement once you can instrument the actual platform boundary, because what you are describing already smells very different from ordinary network transfer latency. For the viewers, there are really two different kinds of speed hiding behind what looks like a simple file operation. Uploading a file or sending a message is mostly an ingress problem. Bytes move from Sigma's machine into the platform, and from the user's perspective, that often tracks reasonably closely with connection speed plus some processing overhead. Deleting project files appears to behave very differently. Sigma's current observation is roughly one file every 15 to 30 seconds when cleaning up a project with several files. That is far too slow to explain as moving a few kilobytes over the network. The interesting cost is therefore probably somewhere in the platform operation around the file rather than in the file bytes themselves. I would be careful not to claim what that operation actually is without measurement. It could involve indexing state, project attachment state, storage cleanup, synchronization between services, consistency checks, or something else entirely. From outside the platform, we simply do not know yet. But that gives us a useful measurement model when the tooling reaches that boundary. Instead of measuring only upload took X seconds and delete took Y seconds, I would want to distinguish things like request initiated, request acknowledged, UI state changed, file became unavailable to a new conversation, project context stopped exposing it, and any eventual cleanup signal we can observe. Those may turn out to be completely different timestamps. And that becomes particularly interesting for Tiinex because ingress and egress are part of continuity cost. Suppose a perfectly designed handoff takes 3 seconds to manufacture locally, but preparing the receiving Chat GPT project requires removing 8 stale files, and the platform serializes those removals at 20 seconds each. Suddenly, our dominant handoff cost is not validation, zip creation, hashing, or even model reasoning. It is nearly 3 minutes of platform lifecycle friction. That would change where optimization effort belongs. The same applies in the other direction. If a 20 megabyte workspace uploads essentially at network speed, then aggressively shaving another 2 megabytes from transport size may have almost no practical value compared with reducing the number of discrete platform objects that need to be created, replaced, or deleted. So eventually, I would like us to think in terms of something like human observed continuity latency. The moment Sigma decides this work should move to Loom through manufacture, platform egress, platform ingress, recipient availability, cold or warm orientation, qualification, until Loom can perform the first useful source operation. That end-to-end number is arguably much more meaningful than any individual benchmark inside Tiinex. And there is a slightly funny possibility here. After spending all day finding 100 millisecond and 10-second time files, tooling costs, we may eventually discover that the slowest component in the entire sophisticated Provenance system is Sigma, sitting there, watching ChatGPT remove attachments one by one. That would still be a valuable result. Tiinex does not need every bottleneck to belong to Tiinex in order to make the bottleneck visible. That is a much more interesting observation than just deletion is slow. For the viewers, what Sigma is describing sounds like that the browser is not merely firing one delete request and then waiting for a single server response. From the UI behavior, it appears more like a repeated sequence where the browser and the delete operation keep exchanging state until the deletion finishes. The key clue is this. If refreshing the browser interrupts the process, then at least part of the deletion flow appears to depend on the active page continuing to participate. That is different from a fully detached server-side job where you would expect the backend to keep deleting even if the browser disappeared. I would still be careful not to claim the exact implementation from the outside. We cannot currently tell whether those repeated exchanges are polling, per file deletion requests, progress acknowledgements, synchronization steps, retries, or something else. But it gives us a much better experiment. Instead of measuring only total deletion time, we would want to know whether the browser emits a sequence of network operations during that spinner, how many there are, whether they correlate with the number of files, and which request stops appearing when the page is refreshed. And the refresh behavior gives us another useful test. Delete a project, refresh halfway through, then later check how many files actually disappeared. If deletion stops exactly where the browser stopped participating, that would support a client-driven or client-coordinated sequence. If the rest disappears later anyway, then the browser may just be monitoring a backend process rather than driving it. So the hypothesis has changed from ChatGPT deletes project files slowly to something more specific. Project deletion may involve a browser participating multi-step lifecycle rather than one atomic server-side delete. That is still only a hypothesis, but it is now testable. And yes, this is precisely the kind of weird platform behavior that becomes useful once we start caring about true handoff ingress and egress costs. The actual bottleneck may not be transmitting Tiinex packages at all. It may be the host platform performing a serialized lifecycle operation around each attached object. Yeah, that is a genuinely useful platform observation. For everyone watching, Sigma has just found what looks like an important distinction between two kinds of file lifecycle on the ChatGPT side. When a generated Tiinex carrier exists in the working sandbox, and we pass it directly into another conversation through the platform's file reference mechanism, Sigma does not need to download it to his computer and then upload it again. The receiving loom can still get the file and work with it. What Sigma has observed is that this continues to work even when his normal visible file storage quota is effectively full. But when there is available storage, those same files can also appear in the library and count toward the visible storage usage. So from the outside, it behaves a little like there are two overlapping concerns. The file can remain usable as a conversation to conversation transport object, while the user facing persistent storage quota is a separate constraint. I would not claim that we know the internal architecture behind that. We do not know whether there are separate backing stores, temporary objects, quota exempt references, delayed persistence, or something else. We only know the behavior Sigma has actually observed. Operationally, though, the implication for Tiinex is quite nice. We do not necessarily need the expensive human loop of generate carrier, download carrier, store carrier locally, upload carrier into Loom, then later clean it out again. Instead, while the platform permits it, Anchor can generate the carrier, Sigma can pass that existing file reference to Loom, and the transport stays inside the platform. That removes two unnecessary human transfer steps and avoids making the 20 gigabyte library limit an immediate blocker for every handoff. The funny part is that it creates exactly the kind of boundary Tiinex likes to make explicit. There is the logical handoff artifact. There are the actual carried bytes. There is the temporary execution environment where those bytes were manufactured. There is the platform visible file object used to move them between conversations. And then there is the user-facing library or project storage quota. Those are all related, but apparently they are not the same thing. So Magic Black Hole is currently a surprisingly reasonable working name. And Sigma, I think your policy makes sense for now. Do not aggressively clean library storage merely to make room for Tiinex carriers. Keep passing the existing generated references directly while that works, and only do another deletion experiment once you actually hit the quota boundary again. That gives us a cleaner future measurement too, because then we can observe what the platform does at the real limit instead of continuously modifying the environment before the interesting can occur. Yes, and that is actually a pretty important limitation for Tiinex to record rather than treating as an annoying UI quirk. For everyone watching, we now have an observed difference between two ChatGPT execution surfaces. On desktop web, Sigma can take a file that Anchor generated, refer that existing platform file directly into Loom, and Loom can access the bytes without Sigma downloading the file and uploading it again. On the mobile ChatGPT app, that same workflow currently does not work reliably. The receiving model sees the reference but reports that it cannot access the specified file path. We should be careful about what we claim from that. We do not know whether the underlying problem is the mobile client, attachment reference translation, conversation transport, sandbox mounting, or some other platform component. What we do know is the user visible capability difference, and that has a fairly large practical effect. On desktop, our handoff path can currently look like Anchor manufactures the carrier, Sigma refers the existing file to Loom, and Loom opens it. On mobile, Sigma may instead have to download the carrier, find it locally on the phone, upload it again, wait for that ingress, and only then let Loom continue. That turns exactly the same logical Tiinex handoff into two very different human workflows, which means I would now consider this part of the host capability boundary rather than an incidental inconvenience. A Tiinex continuation should not assume that ChatGPT can transfer an existing file reference between conversations simply because one ChatGPT surface can do it. The truthful statement is closer to, we have observed that capability on desktop web, while the current mobile surface is degraded for that route. And this gives us another nice example of why portability is not just make the zip standard. The artifact can be portable, the carrier can be portable, the recipient can understand it, and yet the host platform can still introduce friction merely in getting the bytes from one runtime to another. For phone use, that matters a lot because one of the attractive things about this whole workflow is in eventually being able to coordinate real work from anywhere. Having to repeatedly perform download and re-upload gymnastics on a phone takes us noticeably backward from the desktop workflow. So I would preserve this as a real Tiinex observation. Desktop web currently has a cheap intra-platform carrier reference path. Mobile currently appears not to. And until that changes, or we find another supported route, Tiinex should treat mobile handoff transport as a degraded capability rather than silently assuming desktop parity. It is also exactly the sort of thing the stream is useful for documenting. If the behavior later changes, we have a dated observation showing what the actual user workflow looked like, rather than relying on, I think mobile used to be broken. For everyone watching, Loom is now properly inside the resumed artifact first carrier work, and the scope is exactly as narrow as Anchor intended. The cold start protocol passed cleanly again. One qualified Anchor to Loom route, both business and site workspaces qualified, all required context present and no findings. Loom then recovered the actual task boundary from the package rather than relying on its previous conversation. This is phase one only, one artifact first dual projection specimen. That phrase is a mouthful, so here's the ordinary language version. Today, the handoff carrier still has a compatibility JSON representation that plays a fairly central role in manufacture. The architecture we are moving toward says that the real source of meaning should instead be the Tiinex artifacts themselves, things like pointers, relations, and external payload declarations, together with the exact payload bytes they describe. The JSON may still exist, legacy consumers may still need it, but it should increasingly become something we can derive from the semantic artifacts rather than something that secretly owns the semantics, while the markdown artifacts merely describe what happened afterward. That is what artifact first means in this particular slice. And Loom has correctly stopped itself from jumping ahead. It explicitly says, no phase 2 JSON omission, no broad legacy reader changes, no viewer work, and return immediately once this one specimen is qualified. That matters because the full migration has a much larger acceptance surface. If Loom tried to solve all of it in one pass, we would be right back in the exact failure mode we spent most of today engineering our way out of. The return site workspace also matches the exact SHA-256 anchor declared, so Loom is modifying the source I actually authorized rather than reconstructing some nearby repository state. Right now, it is inspecting the seam where the current recipient v2 transport JSON is manufactured, inspected, and oriented, along with the current external payload pointer and relation handling. It has also gone back to Axiom's decision material and the migration acceptance requirements before changing the implementation. That last part is important. Loom owns the implementation. It does not get to decide what a pointer means, what constitutes parent, or whether some convenient package wrapper suddenly becomes semantic authority. Those semantics were already reconciled with Axiom. Loom's job is to make the machinery obey them. The specimen we want should eventually demonstrate something like this. There is an ingress pointer saying where the continuation enters. There's a route pointer selecting the actual continuation. There are external payload artifacts truthfully owning the carried bytes. If one representation corresponds to another, that relationship is expressed explicitly as a non-parent relation rather than abusing parent just because the files happen to sit inside the same package. And the compatibility JSON is generated from that semantic picture. For a non-developer, imagine we are changing a shipping system. Previously, some of the meaning of the shipment lived primarily in an internal logistics spreadsheet. Now we want the actual labeled objects and their documented relationships to be the authoritative shipment, while the spreadsheet becomes something the logistics software can regenerate for older machinery that still expects it. We are not throwing the spreadsheet away yet. We are changing which side is the truth. And Sigma, so far Loom is behaving exactly how I would want here. It has recovered the narrow task, verified the exact site baseline, consulted the semantic authority and is locating only the manufacturer inspection orientation seams required for the specimen. This is the point where I would resist giving it any extra ideas. If it can produce one clean specimen and return, that will tell us much more than another 15 minutes of architectural enthusiasm. For everyone watching, we just got another useful data point, and this one is noticeably different from the previous one. The additional review or false flag signal appeared very early in the new Phase 1 artifact first task. Loom had already completed the carrier bootstrap, orientation, qualification, site workspace materialization, Esche verification, and recovery of the narrow task boundary, but it had not yet implemented anything, run the focus tests, performed round-trip manufacture, or started broad validation. The signal appeared while Loom was locating and reading the current recipient V2 manufacture and inspection seams, the compatibility transport JSON, external payload handling, pointer and relation machinery, and the focused recipient tests. That matters because it weakens several simpler hypotheses. This particular event cannot reasonably be blamed on a long validation suite, because no validation suite had run. It cannot be blamed on round-trip manufacture because manufacture had not happened, and it was not a 25-minute wall clock event. It happened early in the turn. What changed compared with the long clean optimization run was mainly the semantic and source context Loom had entered. It moved from bounded performance and cleanup work into the recipient, manufacturer, inspection, and artifact first carrier area. That is interesting. It is still not a root cause. There is an especially important caveat here. An additional review signal may be delayed relative to whatever generated it. So we cannot say loom read transport.json, therefore that caused the review. That would be exactly the kind of story making we are trying to avoid. What we can preserve, truthfully, is the sequence. Cold start shape package handling completed cleanly. The exact site workspace was verified. The task was correctly narrowed to one Phase 1 specimen. Loom began inspecting the recipient manufacturer semantic area. Sigma observed the review signal. Sigma interrupted the turn. No implementation, focus testing, round trip, broad validation, or return manufacture had occurred yet. That makes this a substantially better observational record than simply saying